Alright, let's continue. Let me open the table of content first. We are still on chapter 18, patching introduction here. We are on homework simulation. Let me open that. Yeah, basically trying to understand how the simulation script here works from the homework simulation. We already take a look at this question. We already take a look at this question too. We already take a look. We are currently taking a look at question 3 with this flag, basically with the page size 1K and address space size 16K and physical memory 32K with verbose flag to give some information about the page table, the virtual page number, I guess, in the page table, and the use flag, basically the percentage of virtual address use, something like that. Let me open that. What is it? Patching linear translate. Okay. This is the script, and I have a few questions previously. Okay, now we are trying to understand this question. Why do we need to left shift the page frame number with page speed? Okay. Guess let me put this in here. Okay. Alright, from the expression, this one. Okay. So why do we need to use left shift with the page frame number? Okay, previously, where is it? I think this one, right? Previously, to get the virtual page number, we need to do the right shift, something like this, right, to get the virtual page number. And this one is the base of the virtual address, the what is it called, the base address, maybe something like that, base virtual address for the page number 10 here. If you take a look, yeah, something like this. In this case, we have the address page size and page size 1K, right? Address page size 16K and page size 1K, we have this what is it, page table, something like that, and 10,240 virtual address is in the virtual page number 10 here. The base, what is it called? The base address, base virtual address in this page number, something like that. So I think we need to do what is it, left shift to get the base address, the base physical address, something like that, for the page frame number. How do I explain that? When we need let me think. Wait a minute. The page frame number is is the index where the page frame or physical memory resides, and to get the base physical address and to get the base address of the physical frame, maybe something like that. Memory, we need to multiply by we need to multiply. Wait. Let me try running the script. Okay. We are using this flag. 1K, 16K, 32K, verbose, and then 5. Page 10. So and we have something like this. We kind of doing something like this. Right? Okay. something like that. Page size. Let's see if can let's see if by page size speeds or page speeds. Like we need to multiply PFN page frame. We need to multiply page frame number by the page size. Is equivalent to base address of the physical memory of the physical frame, I guess. And to get the base address of the physical frame, we need to multiply okay. Now why we need to multiply that? Okay, I assume we need to multiply the page frame number by the page size to to get the starting point, I guess. We need to multiply getting the starting point, maybe something like this. Getting the starting point for page frame number. Why do we need to multiply page frame number by the page size? I assume it is something like getting the starting point for the page frame number, something like this. I mean, do this. Previous obviously is 10, right? From this page table, I guess we have some range. Yeah, the range is 1K, something like that. Wait, or maybe to multiply so that we know how to explain this. Get the base address of the physical frame. Base address. Okay, maybe something like this. Every page frame has the size of page size. Have the size of the page size and have the range of zero until page size -1, I guess. So if we do something like this, for example, become 0, right? 1024. It is, yeah, this page size, right? So the starting address so the starting maybe, yeah, let me put this in here just in case I need that again. But I think this is a better explanation. Every page frame in physical memory has the size of page size and have the range have the range of 0 until page size -1. So the starting address for each page frame is page number multiplied by page size, maybe something like that, multiplied by page size, right? And if it is 19, let's say, okay, something like this. So the starting address for each page frame is page number physical address and also virtual page in virtual address space is the size of page size and have the range of this one. So the starting address for each page is page number multiplied by page size. Either in physical memory or virtual address space. And then and left shift something like this, and left shift by page size bit or bits like this is equivalent to this one. Okay, and page space is equivalent to page size. So PFN left shift page bits is equivalent to PFN multiplied by page size. Okay, something like this. Do we already explain about the page speed here? Kind of, I guess. explain the page speed first. Page speed in here means the exponent the exponent for 2 something like 2 power page speed and left shift by the page size speed or page like this one is equivalent to and then 2 power page speed is equivalent to page size. So the left shift in here is equivalent to this one. That in mind, we need to left shift. Why do we need to left shift page frame number to get the starting or base address of the starting or base address of the page frame and physical memory. Okay, we need to left shift the page frame number to get the starting or base address of the page frame in the physical memory, and that's why we also need to do right shift here to get the virtual page number, something like that. Okay, and then for this question, we need OR bitwise operation after left shift. Okay, I think let me put this here. That's fine. Okay, if I understand correctly, bitwise OR is to set a subset of bits in the value. Let me try, I guess. Okay, we have this one. You get the binary. Can I do this? Okay, looks like I can. 15, okay. And then using the OR bitwise operation, offset is this one, okay. Just to be sure that is the same. Okay. I think something like this. Maybe. We have address space 16K. Not that one. Is it? Nah, I think 14, right? Okay. 14 bit. And this one is 16. Okay. All right. And if I understand correctly, the bitwise operation or something like this. So we need at least one of these to be 1 to result in 1. Other than that, it is 0. Okay. Maybe something like this. 1 0 0. Okay. And then 1. Oh, sorry, this one 0. Maybe something like this. Okay, looks like it is correct. 24 42. Right. 20,422, I mean. Okay. This one is it again. And then okay. So this is the base address, and then what is it called? We add the offset, maybe something like that. Yeah, let me check. Can we do this? Oh, Okay, interesting. So using the OR bitwise operation here is like adding the address, maybe something like that. But we are doing that in bit rather than decimal. Okay, how do I explain this? After we got the base address, the base address for the bits frame number with left shift we add the offset using OR bitwise operation like this. Wait, let me add this as the base address, maybe something like that. This one is offset and this one is what is it? The physical address, maybe something like that. Oh, right, okay. It's like in decimal, maybe something like this. Okay. Okay, right, let me check. Virtual address. Adding some information there. Physical address. Okay. In decimal operation. is what happened here. Basically, we get the base address and then adding the offset with the OR bitwise operation here. Alright. Okay. Yeah, what is XORing? Let me check. Bitwise operation. Yeah, I'm calling the bit operation as bitwise operation. Something like that. Oh, and not XOR and not. Okay. Oh, XOR is to scared. And then how to do that? This is the N, right? If it is N bitwise operation, all the component need to be 1 to be able to result in 1. Other than that, it is 0. Masking specific bits. Okay, extract the bits, right? Checking if a bit is set. Oh, okay. Clearing bits. Okay. Wait. Let's try this one, I guess. Oh, bitwise complement. Oh, okay. Wait, let me check this first. Where is it? I think it is in the PetSmart. Let me add notes again. Complement bitwise operation is a unary operation, works on only one operand. Okay. Operation is a unary operation operator. That change zero to one or and 1 to 0. For example, yeah, let's use this as an example. Okay, something like this. For example, oh, you know what? Let's do this instead. As binary digit like this. And okay. Become means the binary digits become or negative. Okay, maybe something like that. Okay. Hello, Joy. Welcome. Hello, test. Welcome. Okay, in case anyone new in here, I'm currently reading this book, Operating System 3 ECPs, basically trying to understand the operating system, and we are currently on chapter 18, still in homework simulation here, trying to understand how this simulation script, patching linear translate Python script work with this flag, something like this. So yeah, I'm trying to explain what's going on, I guess, with this instruction, something like that. Okay, binary digit this one, and means, and the complement of this means the binary digit become. Okay. Oh, right. Let's just use the binary representation. Okay. Let me put the reference here. that is the complement. Yet there are some multiple complement, I guess. One complement and two complement. We haven't gotten there yet. Okay. Oh, it also works in C. Okay, interesting. Complement negative 12. Okay. A relative operator. Bitwise XOR. Exclusive OR. Okay. The result of bitwise XOR operator is 1 if the corresponding bits of two operands are opposite. It is denoted by, okay. Usually I'm using caret or the symbol for the power, I guess. Power symbol, but it looks like this is representation for the bitwise XOR. Okay. Let me take notes. XOR bitwise operation. Three set of bitwise XOR or exclusive or bitwise operation is 1 if the corresponding bits of two operand are opposite. Okay, let's say we have this binary. Bitwise XOR operation of 12 and 25. Wait. Okay. Oh. 0 and 1. Reset in 1. If it is 0, 0, it is 0. And if it is 1 and 1, it is 0. Oh. Okay. Maybe something like this. Yeah, let me copy this. Okay. Yeah. This one is 0. This one is 1. This one is 1. Okay, and this one is 0. XOR bitwise operation result in 1 if the corresponding bits of two operand are opposite. For example, are opposite. Okay. Reference. Okay, something like this. This is not opposite, right? This is opposite, so 1. This is also opposite, 1 again, and this is 0. Okay, alright. Yeah, I'm kind of curious, what do we use exclusive OR operator here? Okay. Operation used for the OR bitwise operation here, right? We can use this as a what is it called? To add the bit, I guess, something like this, and the % here, we can use this to kind of remove the bit that we don't need. So what is XOR in this case can be used for? Let me check. Not. Oh, bitwise not or bitwise complement. Is that it? Okay. Complement or not? I thought it is different. Okay. Maybe I should put this in here. Okay. Is the mirror reflection okay? A simple but illustrative example used is to invert a grayscale image. Oh, where each pixel is stored as unsigned integer. Okay. Used to determine whether a particular bit is set or clear. Okay. So for the masking, something like that. Given a bit pattern this one, decimal 3, to determine whether the second bit is set, we use a bitwise AND with a pattern containing 1 only in the second bit. Right, something like this. And any non-zero is true, I guess. Because the result is non-zero, we know the second bit is in the original pattern was set. This is often called bit masking. Okay. Right. By analogy, the use of masking tape cover or marks portions that should not be altered or portions that are not of interest. In this case, the zero value marks the bits that are not of interest. Marks the bits that are not of interest. Okay. And also to clear the select bits in which each bit represents an individual Boolean state is an efficient way to store number of Boolean values using as little memory as possible. For example, this bit can be considered a set of 4 flag number from right to left. Oh, okay. The third flag may be created by using a bitwise AND with the pattern that has a 0 only in the third bit. Think this one. Okay. Bitwise OR. Its pair of corresponding bit. Its position is 0 if both bits are 0. Otherwise, the result is 1. May be used to set 1 the selected bits of the register described above. Example, the fourth bit. Okay. May be set by performing bit OR with the pattern with only the 4 bits set. This is decimal 2. Then this one is decimal 8. Maybe set the 4th bit. Oh, so we are reading this from the right, I guess. I assume this is first bit, second bit, third bit, and then fourth bit. Is that it? Third flag are set. With the first and fourth flag are clear, 0, and the second and third flag are set. Second and third flag. Oh, this one. The first and fourth flag are clear from this bit or binary digit, and then second and third. Second is this one, and third is this one. are set. The third flag may be cleared by using a bitwise and with a pattern that has 0 only in the third bit. So we are clearing this one. Wait a minute. We are clearing this one, so only the second flag are set. Okay. Alright. Yeah, what is XOR or exclusive OR usage? May be used to invert selected bits in a register, also called toggle or flip. Any bit may be toggled by XORing it with 1. For example, given the bit pattern, this one, the second and fourth bit may be toggled by a bitwise XOR with a bit pattern containing 1 in the second and fourth position. Given the bit pattern, this one, the second and fourth bit may be toggled by a bitwise XOR with a pattern containing 1. Okay, we have this one. We want to toggle the second and fourth bit, the second and the fourth bit. Again, we are reading this from the right. First, second, third, and then fourth. Okay. Oh, interesting. Right, if we are using only OR, this one would be 1, not 0. But we are toggling this off, I assume, something like this. 0 is off or false, and then 1 is true or on. So this one becoming 0, and the one that is 0 becoming 1. Okay, this technique may be used to manipulate bit patterns representing set of Boolean state. The XOR can be used to toggle the bit the bit, maybe something like this. Let me also put this in the reference here. Okay. Assembly language programmer and optimizing compiler sometimes use XOR as a shortcut to setting the value of the register to 0. Oh, okay. Performing XOR on a value against itself always yields 0, and on many architectures architecture, this operation requires fewer clock cycles and less memory than loading a zero value and saving it to the register. Oh, interesting. Requires fewer clock cycles and less memory than loading a zero value and saving it to the register. If the set of bit string of fixed length n, for example machine word, and that is machine word. What is machine word? A word is a fixed size datum handled as the natural or historical unit of data by the instruction set or the hardware of a processor. The number of bits or digits in a word is an important character of any specific processor design or computer architecture. Datum. What is datum? Let me check. Datum. Oh, okay. Data. Alright. Is thought of as n-dimensional vector space. Okay. Well, in case anyone wants to understand this, go right ahead. Of bits rather than a numerical quantity. The digits are moved or shifted. Okay. Register in a computer process have a fixed width, so some bit will be shifted out of the register at one end while the same number of bits are shifted in from the other end. The difference lies in how they determine the values of the shifted in bits. Bit addressing. If the width of the register, is larger than the number of bits of the smallest addressable unit, frequently called byte, the shift operation induces an addressing scheme from the byte to the bits, thereby the orientation left and right are taken from the standard writing of number in place value notation, such that a left shift increase and right shift decrease the value of the number. If the left digits are read first, this makes up a big endian orientation, disregarding the boundaries effect at both ends of the register. Arithmetic and logical shift operations behave the same, and a shift by 8-bit position transport the bit pattern by 1 byte position in the following way. Okay. Oh. So left shift and right shift depend on the ordering, I guess. If the left digits are read first. Oh. The left digits are read first. So I'm assuming little endian in here means that we are reading from the right Instead, the orientation left and right are taken from the standard writing of numbers in a place value notation, also known positional notation, also known as place value notation, is the property of a numerical system that the value represented by its symbol in a written numeral depends not only on its appearance but also on its position. Okay. Such that a left shift increase and right shift decrease the value of the number if the such that a left shift increase and a right shift decrease the value of the number. Standard writing of number. Let me try opening this case. Standard writing of number. I'm still not sure what this means. Standard writing of number. If the left digit are read first, this makes up a big endian orientation. The order in which byte within a word data type are transmitted over a data communication medium or address in computer memory, counting only byte significant. Bit addressing. Well, you know what? Maybe we will take a look at this on the next session. I mean, it looks like whether left or right shift increase or decrease depending on the bit ordering, something like that. Is there any table of content here? Bit shift, bit addressing. Okay. Let's continue this on the next session. Okay, maybe I should add this question, I guess. this left or right shift depends on the order of how to read the beats, maybe something like this, and then putting the reference here. Okay, wait a minute, not that one, but this one. Okay, let's take a look at this on the next session. Okay, why is it that in XOR true plus true was false? Wait, what? True plus true, I think equal false, and then false plus false equal false. Is that what you mean under lines? Yeah, I'm not really sure. Maybe that is part of the exclusive conjunction here. Okay, no, of course. Yeah, maybe part of this one. Oh wait, no, not that one. Yeah, well, if you're curious, maybe we can take a look at this on the next session too. What is exclusive OR? Maybe something like that. Exclusive OR. And then looking at this. Okay. Alright. Wait, let me copy this in the chat, I guess. Okay, so maybe we will take a look at this question on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.